Today, lesson 26A, interpreting graphs. Yesterday, we spent some time talking about nonlinear functions. And today we continue with that theme of graphs that are not necessarily linear. So today we're going to represent qualitative relationships graphically, and we're also going to analyze that graph, and then we'll be able to verbally justify where the graph is increasing or decreasing. So we're going to take situations, and as you can already see from your notes, these situations are not linear. And we may have a graph and we have to interpret what that means, or we may have a situation and we have to sort of figure out what that graph is going to look like. And one of the things we're going to be talking about is when a graph is increasing or constant or decreasing. Okay? So a little bit of background knowledge. Discrete relations are ones that we don't necessarily connect the ordered pairs together, because what's in between them doesn't make sense. And back when we talked about this, I gave you the example of the number of students in this class. That's a discrete relationship because you can't have half a student. A continuous one is where all the points in between also make sense, and so that's where you connect all of your points together. We also talked about independent and dependent variables, and we reviewed proportional relationships and how tables and equations and graphs all are interrelated, and once again, sometimes it makes sense to connect the dots together and sometimes it does not. In this situation, it didn't. Yesterday, we talked about some nonlinear functions like absolute value functions that all look like V's or upside down V's. And remember, anytime that happens, at least as of right now, we need to pick the inputs from 2 to -2. Now, let's interpret this graph from yesterday on when it is increasing and when it is decreasing. Because until you've actually seen this, some people interpret them backwards. So when I look at this graph from left to right, to me, the graph is going this direction, and then it's going that direction right there. And I realize that there's an arrow there, but the arrow just means it goes infinitely in both directions. But this graph, once again, is going from left to right, this direction, and then this direction. So what that means is that it is decreasing in this direction, and it is increasing in that direction. Okay? Increasing, we call that from -infinity to 0, and then from 0 to infinity, it is increasing. And when you get to more advanced math classes, you have to define those in terms of where it is increasing and where it is decreasing. So decreasing from there to there, increasing from there to there. Here's another graph from yesterday. In this graph, it is increasing from there to there, going uphill from there to there, and then decreasing the rest of the graph. So once again, increasing from there to there, decreasing from there to there. You might think of it as uphill and downhill if that makes it easier for you. All right, here's the first problem for today. We are comparing a horse's time versus its speed. I know that by looking at the x-axis and the y-axis. And here is an explanation over here on exactly what is happening. So the very first part of this is the horse is walking at a constant speed for 10 minutes. How do I know that it's a constant speed? Because the speed doesn't change. It looks like it's about maybe 3 miles per hour right there. How do I know it's for 10 minutes? Because this is the time axis right there. So you can see from 0 to 10 minutes. The next part, the speed is increasing over the next 7 minutes. How do I know it's increasing? The speed is increasing because the speed is going uphill. How do I know that it's for 7 minutes? Well, because on our time axis, it started at 10 and it's going till about 17. That's 7 minutes from there to there. And by the way, as I'm doing this, you should be drawing arrows like I'm doing in your notes. All right, the next part is it gallops at a constant rate for 20 minutes. How do I know it's constant? Because the speed is staying the same. It's level. How do I know it's for 20 minutes? Well, just like all the other ones, from here to here, that's about 20 minutes. The next part is slows down for the next 3 minutes. That's where it's decreasing. The speed is getting less and less from left to right. And it's 3 minutes because of what we've already talked about. And then it walks at a constant pace for 10 minutes. All right, so what if I take this same exact problem, but I interpret it a little differently? Instead of comparing the horse's time versus its speed, and by the way, I've already kind of talked about that it's increasing from there to there and decreasing from there to there and constant here. But what if I change the time versus speed? What if I change that to the time versus the distance that the horse is from the entrance? So all I've done is I've changed what I'm looking at or what I'm interpreting here. And when you do that, the graph looks totally different. But over here, I'm doing everything exactly the same way. So the horse walks at a constant speed for the first 10 minutes. Constant speed, so that means the speed is on a straight line, but it's moving away from the entrance. So that's why there's a distance there. The second part, the speed increases over the next 7 minutes. So if the speed is increasing, that means it better be going uphill a little faster or a little quicker. That's a speed increase. Now it's going to gallop at a constant rate for 20 minutes. Well, that means it just continues at the pace that it was at. It doesn't speed up. It doesn't slow down. By the way, if the horse sped up, it would look like this, a little steeper. If the horse slowed down, then it would look more like this. We're talking about slope when we're talking about things like that. All right, then it slowed down for the next 3 minutes. But notice it's still moving away from the entrance, so that's why it keeps going further and further to the right on the graph. Now I'm going to add one new step here. The horse then walks back to the entrance, which takes 10 minutes. Back to the entrance means the distance from the entrance is 0, and right there represents a distance of 0. So I took and changed what we were looking at, and the graph looked totally different. And so we have to keep those things in mind with what we're doing today. All right, so we have a couple of multiple choice questions here. Number 1, the height of a tree increases over time, but not at a constant rate. Which graph best shows this? Is it A or is it B? Just say it. B. It's definitely B. Trees, when you plant them, they grow very quickly, and then as time goes on, they kind of get to a height, and then they barely grow after that time period. So that's why it kind of levels off like that. It does keep getting taller, but at a very slow rate. All right, here is number 2. The dimensions of the basketball court have changed over the years. However, the height of the basket has not changed. Now, a lot of people over the last 10 years have wanted to see that change, but it hasn't changed yet. So which graph best shows this? A or B? Which one? A, because we're talking about the height of the basket. It's constant. It has not changed. All right, so here's the first problem that we're actually going to do together. I'm giving you a situation here, and we have to kind of figure out what this situation will look like in terms of the graph. So it says, Jared parked his car in the supermarket parking lot and walked 40 feet into the store and to the customer service counter where he waited in line to pay his electric bill. Jared then walked 60 feet to the back of the store to get 2 gallons of milk and walked 50 feet to the checkout near the front of the store to pay for them. After waiting his turn and paying for the milk, he walked back 50 feet to his car. Sketch a graph to show Jared's distance from his car as a function over time. So we are comparing the amount of time to the distance from his car. Now, we're going to do this one together. Now, I've already mapped it all out for you, and then we're going to go through it piece by piece, and I'll show you why the graph should look like that. And as we're doing it, I want you to add each piece to your graph. So the first thing it says in this problem is that he walked from his car 40 feet into the store. So he's moving away from his car into the store. He walked 40 feet. That's why the graph is up to 40. From there, it said that he waits in line to pay his electric bill. So when he's waiting in line, he's not moving any further away from the car, which is why it's still, as you can see right here, it's still 40 feet from the car. The problem goes on to say from there he walked 60 feet to the back of the store to get 2 gallons of milk. Well, that would be represented by that part right there. He's moving further away from his car. After he gets the milk, he then walks 50 feet to the checkout near the front of the store to pay for them, which means he's getting closer to his car. He was 100 feet from his car. He's now 50 feet from his car. All right, so then after waiting his turn, which means he's waiting in line, so he hasn't moved any further away from his car, but time has gone by. And then after he pays for the milk, he walks 50 feet back to his car, which takes the distance back down to 0. Okay? So here's what you're going to do. You're going to take a look at number 4. You're going to read the problem. And it does say in number 4 to sketch a graph, so it doesn't have to be perfect, but the shape of it should look very similar to what it is actually supposed to look like. So here is number 4. And by the way, I'm asking whether the graph is increasing or decreasing. I think that's fairly obvious at this point. All right, so number 4 says, Darcy traveled 22 miles from her house to the Peterman's house, where she babysat for 1 hour. After babysitting, she traveled 8 miles further to the deli to buy a sandwich. After eating her sandwich, which you have to assume she ate the sandwich at the deli, she returned home. Sketch a graph to show Darcy's distance from her house as a function over time. So right now you have this blank graph that looks something like this. So I'd like you to sketch it out, and then I'll have you compare that with your shoulder partner. Darcy traveled 22 miles from her house. That means the distance from her house to where she's going increases. So, should look like this. The first part, traveling from her house. Then, she babysat for 1 hour, so she's not moving any further away from her house. She drives to the deli. She eats her sandwich. She then drives home, increasing from here to here and there to there, decreasing from there to there. Both of these areas, of course, are constant. All right, let's take a look at number 5. Here's what I want you to do. One of them is obvious. The other one is obvious that it's wrong. Discuss with your shoulder partner really quickly what would have to happen for the one that's not correct to actually happen. Answer is definitely A. All right, so now we're going to go backwards. Now I'm going to give you a graph, and we need to kind of figure out what that is trying to say in terms of what the graph looks like. So Lucas, not the Lucas in this class, but Lucas is driving to work. The graph below, that's the 6th grade bell. The graph below shows Lucas's speed over time, and that's the thing that you need to keep in mind. We're comparing the amount of time to the speed. What I want you to do is to come up with a quick story. It doesn't have to be elaborate. I'm not asking for an essay. Create a story problem which this graph might represent. I'm going to give you about a minute to 2 minutes by yourself, and then we'll kind of compare what we have with our shoulder partner, and then we'll talk about it. All right, so I heard some good things there. There are many possible things that you could write. Here's one possible thing. Lucas increases his speed for 8 seconds until he reaches a speed of 44 miles per hour. Now, this is a little more elaborate than I'm expecting you to do, okay? Just keep that in mind. He maintains a constant speed for 44 miles per hour for 4 seconds. Now, a couple of things that were talked about: increased and constant so far. Then he decreases his speed for 4 seconds until he stops. Now, how do I know that he stopped? Because his speed right there is 0. He then accelerates and increases his speed for 8 seconds until he reaches 60 miles per hour. How do I know he increased? Because of that right there. How do I know it's 60 miles per hour? Because that's the speed right there. Then he drives at a constant speed of 60 miles per hour, constant speed for 16 seconds. All right. Lots of possible things that you could have written for that one. Let's take a look at number 7. Same idea. Read it to yourself. Write a quick little story. And then we'll compare with our shoulder partner. In an earlier problem, we had that tree problem. And we talked about the fact that when you plant a new tree, it grows really, really quickly. And then over time, the amount or the rate at which it grows slows down. Same thing when a new video game, or for that matter, any new product that comes out, a bunch are sold really, really quickly, and then over time, they still keep selling, but the rate at which they're selling it slows down. And so basically, that's what I heard most of you talk about. All right, number 8. Here's another one. I'm not going to make you do this one, but what we're comparing in this one is time versus distance. And so a family is taking a road trip to visit their family in Las Vegas. So they're leaving home, which looks like from the graph is 450 miles from Las Vegas. They're traveling to Las Vegas. And so a story that may represent that would be something like this. Sam and his family live 450 miles from Las Vegas. They travel for 5 hours at a constant speed. I know it's a constant speed because it's a linear line segment right there. It's a line segment. And then they stop to eat lunch for 1 hour. So therefore, they're not getting any closer to their family's house. And then they travel at a constant speed of 25 miles per hour for the last 3 hours. And then they arrive at the house, which of course has a distance of 0. All right, we are finished.